All right, you guys. So here are the 2.7 video notes. I'm going to go through this pretty fast. There won't be as much explanation and all that kind of stuff as the notes in class because it'll be like a 70-minute video and no one wants to watch that. Okay, so solving related rate problems. Related rate problems are essentially something that appears when you have elements of a expression or some sort of object or shape that are changing with respect to time, and you know one of them and you want to find out how that element changing affects another element. They're pretty straightforward, but they can get really, really complex if you don't actually know what's going on and how to connect all the elements together. So the steps are pretty easy. Identify all of the given rates. So read through the problem, identify everything given and the values with them, and also determine what the rate is to be determined. Then you go through and make a sketch if possible. Your next step is to write an equation involving the variables and values from step number 1. Then you implicitly differentiate both sides of the equation with respect to another variable, usually time t. After completing step 3, you substitute into the resultant equation all known values for the variables and their rates of change, and then solve for the required rate of change. The big thing about this, you guys, is that when you go through and solve these problems, you have to be extra careful to only plug values in if they're something that is moving at the very end after you take the derivative. Otherwise, stuff doesn't work. All right, so our first example involves air being pumped into a spherical balloon at the rate of 4.2 cubic feet per minute. And it says find the rate of change of the radius when the radius is 2 feet. So I always like to start this off. You can draw a picture here, but it's just a sphere, so I'm not going to draw a sphere. I start off by going, what am I given? And it looks like I'm being given a rate of 4.5 cubic feet per minute. And this tells me that the volume is changing. Okay, this is volume changing. Okay, and I know it's a volume because it's cubic feet. Cubic feet is volume and it's per minute. So when you write these down, I always like to write down given, and then I like to actually write down the expression. And I use the notation given to us by calculus. So the rate of change of volume is dV dt. And this is given to us. It's 4.5 feet cubed per minute. And then it says find the rate of change of the radius when the radius is 2 feet. So what it's asking us to find, so it says find dr dt, the rate of change of the radius with respect to time. And then I like to say when r is equal to 2. Or sometimes I say at instead of n. When, it doesn't matter. So these are what we're going through and doing. And then once you have what you've written down, you look at them and you go, okay, so my major player variables are V and R. And do I have anything that relates the volume of a sphere to the radius? And conveniently, I do. It's the nice formula. V is equal to 4/3 pi r cubed. Okay, so it's V equals 4/3 pi r cubed. And when we look at this equation, I see that there are my two variables in interest, there's no extra variables, and a bunch of constants. And that's really the optimal situation. If you have extra variables, you're probably going to have to do some extra stuff to get rid of them. Once you're here, what we're going to do is we're going to take the derivative with respect to time of this equation. Okay, so when we take the derivative of v with respect to t, we get dv dt. And we take, so this 4 pi over 3, this just exists here, so it's 4 pi over 3 times the derivative of r cubed, which is going to be 3r squared, and then times dr dt. This is all implicit differentiation that you guys should know how to do at this point. All right, the nice thing here is these things cancel out, and I end up with this being equal to 4 pi r squared times dr dt. Okay. Now what we're going to do is we're going to go through and do a substitution for our original expressions. I know that dv dt is actually 4.5. was given to us, and I know this is going to be equal to 4 pi, and then it's r squared. So r squared is going to be 2 squared, because it's at r equals 2, times dr dt. And then to find dr dt, you just solve using algebra. So we're going to divide both sides by this now 16 pi. So we get 4.5 divided by 16 pi. And this is going to be equal to our dr dt, which is equal to, I'm using a calculator right now, you guys. I'm not doing this in my head. Divided by 16 pi. This is going to give us 0.88. And we'll round up to 4. And it's going to be feet per minute, because we're down to a radius. So this is a radius, and radius does not have a squared or anything. So this is how you do these problems. It's a process. It's a step-by-step kind of thing that you go through and do. And the big piece is making sure that you're solving for the given variables correctly. Connecting them, making sure you have given, having all the stuff that you want to find together. Let's look at another problem. Okay, so this one's nice. It gives us a little picture right away. There's a airplane flying on a flight path that will take it directly over a radar tracking station, as shown in the figure. The airplane is flying at a constant altitude of 6 miles. So this is constant, which means it is not changing. So we can fix it. It is fixed at 6. We do not need to worry about any rates of change of the height, because it told us it's constant. If s is decreasing at a rate of 400 miles per hour when s is equal to 10 miles, what is the speed of the plane? Okay, so obviously as the plane goes this way, this s distance and this x distance are going to begin to decrease. The x distance will go down and the s distance will decrease until it's vertically right above it, and then it will begin to increase once again. So given ds dt is equal to negative 400 miles per hour. And this is when, so at s equals 10, we want to go through and find dx dt, the speed of the plane, so the rate of change of how fast it's moving on the ground. And we've labeled this variable x, so it's the rate of change of x. So dx dt, this is what we want to find. And the thing about this is we want to make sure we're finding it at an s value. Well, I know s is equal to, when s is 10, this is 400, and we want to find the speed of the plane at that same time. If we go through and write down a relationship between these two variables and the side 6, we should see this is a right triangle, and we can write it down. It's going to be s squared is equal to x squared minus 6 squared. All right, if we go through and take the derivative now, so the derivative with respect to t of these things, I end up with 2s ds dt is equal to 2x dx dt. All right, and now we have an issue here because I have this x value as well. And the question is, well, what is x when s is 10? So what is x when s is 10? Okay, and the nice thing is we can use that same formula. I know it's going to be 10 squared is equal to x squared minus 6 squared, and hopefully, sorry, plus 6 squared. Oof, I messed this up completely. Plus 6 squared. Forgot the Pythagorean theorem, you guys. And if we look at this, we should be able to see that x is equal to 8 when s is 10. Okay, now this is the value we're going to plug in here for x, and then we already know s is 10 and we know ds dt. So we write everything down, so it's 2 times 10 times ds dt, which is negative 400, is equal to 2 times 8 dx dt. Now I'm going to go through and do some division, and I should end up with the expression dx dt is equal to 2 times 10 times negative 400 divided by 2 times 8. And this is actually something I would expect you guys to be able to simplify. I do this wacky thing where I cross out all these factors just to make it easier on me, and then I know this is 400 and 100, so I cross it out and get negative 100. This goes away, and I end up with negative 500, and then the units are still going to be in miles per hour. But remember, it asks for the speed of the plane. Okay, so speed of the plane, so our speed dx dt is equal to 500 mph. Let's just put a little box around that right there. So you got to be real careful when you set up these equations for knowing when you're going to end up with a variable. The general rule is that unless this is just a variable by itself, so if it was just x, it's going to go away, but because it's x squared, I'm going to end up with an x in my derivative. And that's kind of the intuition that you guys need to carry into these problems. Knowing that, it's beneficial to know how to go through and necessary to know how to go through and solve for this x equals 8. Here's another problem. So it says at a sand and gravel plant, sand is falling off of a conveyor onto a conical pile. Okay, so a conical pile looks like a cone. All right, so we can draw a conveyor belt right here, and there's some sand, and it's falling off, and it's falling into a cone. Okay, so here's our cone. It's harder to draw this than you guys would think. So let's make a better cone. All right, so here's my cone like this. Okay, and then you can draw the little curve thing to give it some dimension. This is a terrible cone. And then it says the diameter of the base, so it's falling off of a conveyor onto a conical pile at a rate of 10 cubic feet per minute. So this tells me that what am I given is that dv dt is equal to 10 feet cubed per minute, and that the diameter of the base is approximately 3 times the altitude. So let's write that down. Is equal to 3, and then the altitude is really just the height. And it says at what rate is the height of the pile changing, so that means we're trying to find dh dt. So at what rate is the height of the pile changing, so that's dh dt, when h is equal to 15. So at h equals 15. Now, once you have all this stuff down, dv dt and dh dt, remember, because this is the volume of a cone, we have some nice formulas that go through and do this. It's v equals 1/3 pi r squared times h. Okay, and the issue here is we have this r squared, and this r squared is messing this up because when I go through and take the derivative of this function with respect to t, I'm going to end up with a dr dt and an r, and those are not values that were given to me. I could go through and find r, but I'll never be able to find dr dt easily in this situation. So instead, what you go through and do is you work with this original little extra bit right here. I know the diameter is equal to 3 times h, and I know that diameter is equal to 2 times r. So therefore, I know r is equal to 3h over 2. And I'm going to take this value and substitute in for r, eliminating the r value in favor of h. Then I'm just going to end up with some dh dt's and some h's and all that. And that's what I want. Simplify it as much as possible. So this is equal to pi over 3 times 3h over 2 squared times h. I'm going to simplify this bit a bit. So 3 squared is 9. 9 divided by 3 is going to be 3 pi over 4, because it's going to be 2 squared. My 3's are all canceled out. And then times h squared times h. So that's going to be h to the third. So this h squared here times h. So this is v equals that. I'm then going to take the derivative right here. So the derivative with respect to t. With respect to t. Okay, I take the derivative with respect to t, and I end up with, I'm going to draw this up right here, dv dt is equal to, it's going to be 9 pi over 4 again, times h squared times dh dt. Now that we're here, what we're going to go through and do is substitute in our variables. And I do a quick check. I have a dv/dt, I have an h, and I have a dh/dt. dh/dt is what I'm trying to find. dv/dt is something that was given, and it's at h equals 15. So I have all the elements I need. So I get 10 is equal to 9 pi over 4 times 15 squared times dh dt. Solve for dh dt. I see dh dt is equal to 40 divided by 9 pi times 15 squared. With this, we're going to throw this into a calculator to get a decimal approximation. So 40 divided by 9 pi times 15 squared. And this gives us approximately 0.00629. And then our units, because we're going down to a height, that's going to be in feet, and then per minute, because we're not changing our timestamp. These are generally the, I won't say highest level of complexity, but there's a lot of algebraic manipulations going on here. You have to be very aware when you're doing these problems of what your derivative is going to give you. When you notice you're going to get a dr dt, you better have some way to solve and get rid of it. Otherwise, you're going to really struggle. This is another fantastic problem that's pretty classic. It says a 16-foot ladder is leaning against the wall. So I'm going to start off right away by drawing a wall right here with a ladder leaning against it. All right, this ladder is 16 feet. That is static and not moving. It's not changing. It says the bottom of the ladder is 5 feet from the wall at time t equals 0, and it begins to slide away from the wall at a rate of 3 feet per second. So this begins to move away at 3 feet per second, which means that this distance right here is changing. So I'm going to give this the variable x. And then if you think about it, if the bottom of the ladder begins to move away, this top of the ladder right here is going to slide down against the wall. And it says find the velocity of the top of the ladder at time t equals 1. So we're seeing what is this distance here doing as the bottom moves out. With those variables, hopefully you guys can see there's a really, really nice Pythagorean relationship with this. But we have a little bit more to go through and do. So again, it's always good to write down given, my given, and because I've labeled everything with variables, and this is x, I'm going to say dx dt, right, is equal to 3 feet per second. Okay, and then I want to find dy dt, find dy dt at, I don't know where I want to find this at actually. That's kind of the confusing part. Because it's not telling me, it's telling me at a time, but I don't have any knowledge of the relationship between time and distance. So what we do is you rely on the initial condition. So it says that times t equals 0, at t equals 0, x is equal to 5. And we know that x is changing at a rate of 3 feet per second. So then I know that at times t equals 1, x is going to be 5, and then it's increased or slid away 3 feet over that second, so plus 3, which is equal to 8. So at times t equals 1, x is 8. And when I know at this moment x is 8, I can go through and calculate y. I know that 16 squared is going to be equal to x squared plus y squared. And I know x squared in this case is going to be 8. So it's going to be 16 squared is equal to 8 squared plus y squared. And when I go through and do this, I'm going to end up with y is equal to the square root of 192. Okay, using that square root of 192 and the point x equals 8. So it's at x equals 8, y equals the square root of 192. Right, and the nice thing is I actually know that I need a x and a y because of what my equation looks like. I know that the relationship between these is 16 squared is equal to x squared plus y squared. And I know when I take the derivative of this expression with respect to t, I'm going to end up with 0 is equal to 2x dx dt plus 2y dy dt. And then I kind of have everything that I need. I know dx dt is 3 feet. I know x is 8. I know y is 192. I knew I needed to find these two x's and y's because of where it is. I think the trickiest element of this problem was this component up here in the upper right, where we're going through and calculating our x and y at times t equals 1. But from here, it's very easy. Just go plug in values. 2 times 8 times dx dt, which is 3, plus 2 times y, which is the square root of 192, times dy dt. We can now solve for dy dt. I know dy dt is equal to negative 2 times 8 times 3, which I'm just going to write it down. I don't know why I started writing down the actual operation. This is going to be 48 divided by 2 times the square root of 192. So this is going to be negative 24 divided by the square root of 192. And if we get a decimal approximation for this, we should see it's a wonderful, adorable little value. It's actually going to be the square root of 3, which is kind of nice. But it's going to be 1, so 1.732. And then my units are going to be feet per second. Okay, and a lot of this related rate stuff is kind of fun to think about. So if you've ever seen a ladder slide down a wall, so it's sliding down, it's not completely disconnected from it. So the bottom is sliding, everything's connected. So it's not just gravity acting on it, there's all sorts of friction and everything as well. If you watch a ladder do that, it's going to fall faster the closer it gets to the ground. So it is actually a good question to ask. Here's another one that's also a fantastic little question. And very interesting too. So it says a man who is 6 feet tall is walking away from a light pole. So I always start with drawing a picture. Here's my light pole right here. There's the light. And then there's a man who's 6 feet tall and the light pole is 30 feet tall. So this is 30. Here's my man down here. Okay, he's just 6 feet tall from here to here. And then he's actually casting a shadow. So here's my shadow right here. It's not a very good shadow, but you get the idea. And what we're doing is we're actually creating a triangle. I didn't do this very well. My practice with drawing with the tablet is not very good anymore, you guys. So it looks like this. That's good enough. You guys get the idea. And then we also have a distance here to the man. So this is the man. This is the shadow like this, and so on and so forth. Okay, so it says he's walking away from the light pole at a rate of 2 feet per second. So he's going this way at 2 feet per second. Okay, so the question is, what is actually happening here? Well, this distance from here to where the man is at is approximately x. Okay, we don't know what it is. We know at one point he's 24 feet from the pole, but we don't actually know what is going on here because it's changing. This x value is changing. So what we do then is we go through and let's label this distance to be y. The length of his shadow is y. Okay, because that is changing as well. It's increasing. And this actually gives me two individual triangles. I know that x plus y and 30 is a triangle. Okay, and then I also have another triangle inside of this that's 6 and y. So because of the way triangles work, I know that these things are going to be proportional. So I know that y over x plus y is going to be equal to 6 over 30. And these are in the same thing, so I know these things are going to be true. So now that we got this, I'm going to multiply, so I get 3y is equal to 6 times x plus y. Okay, 6 times x plus y. Oops, sorry, not 3y, 30y right there. And then I'm going to divide everything by 6, and I get 5y is equal to x plus y. I'm going to subtract that over, and I'm going to end up with 4y is equal to x. Once we're here, this is actually super straightforward. I'm just going to go through and take the derivative of this expression. So the derivative with respect to time of this is going to be equal to 4 times dy dt is equal to dx dt. And I happen to know dx, I forgot to write those down, given is that dx dt is equal to 2. So I know then I want to find dy dt. Okay, and the beauty of this is we didn't actually need to use this 24 feet from the pole at all. Okay, because when you plug this in, I get 4 dy dt is equal to 2. 4 dy dt is equal to 2. And I know that dy dt then is equal to 1/2 feet per second, which is pretty cool. You don't even need to use some of these extra bits and pieces. It doesn't actually matter how far this person is from the pole with that 24. It doesn't have any component to this problem, which is pretty exciting. So then we go through and we have to answer the second question. How fast is the tip of his shadow moving when he is 24 feet from the pole? This is also not super crazy. So if you think about it, okay, so here's B over here. If this guy is right here and he's walking away, and if this is his speed this way is 2 feet per second, so this way he's moving 2 feet per second. So x is changing at 2 feet per second. And then we know now that y is changing at 0.5 feet per second. Okay, y is going this way at 0.5 feet per second. Then what's the tip of his shadow moving at? Well, it's just x plus y. It's just going to be x plus y. And that's pretty much it. So the speed of his shadow, or the tip of his shadow, is going to be moving at 2.5 feet per second. 2.5 feet per second. That's just logic there. You don't even need to do much math at all. And that's really what I love about these problems, is that there's not a lot of like heavy math going on other than some basic relationships that you guys have all learned and know perfectly. Here's the last problem of the notes. Thank you guys for bearing with me. It looks like we're at 28 minutes. Let's see how long it'll take to do this. So let's think it's a piece of ice cut in the shape of a cube, melts uniformly, so perfectly melts so that its volume decreases at 3 centimeters per second. So one of my given is that dv dt is equal to 3 centimeters cubed per second. How fast is its surface area decreasing when the edge of the cube is 5 centimeters? We're going to call that dA sub s of dt. So a sub s is going to be my surface area. So this is what we're going to find. And this is at my side, which I'm going to call s, is equal to 5. All right, now I have to go through and write a formula that relates velocity and surface area. I know the not the velocity, volume and surface area. So I know the volume of a cube is equal to the side cubed. And I know the surface area, A sub s, is equal to 6 times the side squared, because there's 6 sides with an area of side squared. And you have some options here. You could choose to solve for s. So s is equal to the cube root of v, and substitute in for the surface area formula, but that sounds awful. I don't want to do that at all. So instead, what I'm going to do is I'm going to do dv dt. So I'm going to take the derivative of my velocity equation is equal to 3s squared ds dt. And I'm going to solve for ds dt because I know dv dt is equal to 3. So this is equals 3 times, it's going to be 5 squared times ds dt. Solve for ds dt, and I should see that ds dt is equal to 1 over 25. This is going to be centimeters per second. All right, I'm going to come over here now to my surface area formula and take the derivative with respect to time of this. I'm going to end up with dA sub s dt. So the rate of change of the surface area with respect to time is equal to 12s ds dt. And my s is still at 5. So I get dA sub s dt is equal to 12 times 5 times ds dt when s is 5, which we now know is 1/25. So it's times 1/25. And this is going to be equal to 12 over 5 centimeters squared per second. Okay, you got to make sure you put those units on there. There we go. Those are the notes. These problems are pretty complex. I don't think they're too crazy out there, but getting all the components together can be pretty challenging. I'm sorry you now have a 32-minute video to watch. I'm also going to post a practice for you guys to go through and do, so that practice will be pretty entertaining. There's going to be a couple of homework problems, and then when we come back, we're going to work through some more problems together. All right, thank you guys so much for taking the time to watch, and carefully take these notes and do the practice before you return.